physics fans, Mr. G here. Last lesson we talked about this idea of speed and velocity, yet we really glossed over the idea of how do you get up to speed and how do you slow down once you get up to that speed. And the answer, very simply, is uniform accelerated motion. So let's start off by defining acceleration. Acceleration is the rate at which an object changes its velocity, and it's measured in meters per second squared, as we found out in earlier lessons. It doesn't matter if we're speeding up or slowing down, acceleration is responsible for that speed up and slow down. Like velocity, acceleration is a vector, defined by a fairly simple equation we'll talk about in a second, but the important thing I need you to know is that anytime an object's velocity is changing, it is accelerating. So we have here a nice little applet to show us three different cars in motion. The car at the top, the red car, well, that one's moving uniformly, so you'll notice that each motion forward is the exact same distance. If you take a look at the green car, it starts off much slower, but you can tell by the end it actually gets up to the same speed as the red car. And finally, the blue car at the bottom starts off behind, but notice that it zooms away at the end. The green car and the blue car are obviously experiencing acceleration. Acceleration can be described with a very simple equation, and we take a look at it right here. Acceleration, which is a vector, I'll put the arrow over top, is equal to the change in velocity, also a vector, let's go ahead and put an arrow on top, divided by time. We'll recall that delta means change in, so that is equal to our velocity final minus our velocity initial. T, of course, is time, which is a scalar, and as I said, acceleration is our pretty little vector. So, very, very similar to the previous equation on velocity. Obviously, we're dealing with velocity instead of distance. So let's use this in a couple of questions. Let's start off with an easy one. A sprinter starts from rest and reaches a speed of 12 meters per second in 4.25 seconds. Find his acceleration. So a word you're going to see a lot is this idea of rest, and all that means is that your initial velocity is equal to 0. So one of the things I'm going to get you guys to start doing is writing out what you know and what you need. So we know that our initial velocity is 0. We know that our final velocity is going to be 12 meters per second. We know that our time is equal to 4.25 seconds. And what are we looking for? We're looking for acceleration. So I'm going to put a big question mark on that. Now, we only know one equation to solve this, so let's do it. Our acceleration is equal to our change in velocity over time, which is equal to, well, VF is 12 meters per second. Subtract VI, which is 0. Divided by our time, which is 4.25, and we're going to end up with a value equal to 2.8 meters per second. Again, I'll say squared. Again, I'll say I dropped the units when I was actually plugging the numbers in. It's up to you whether to do that or not. I knew that all my numbers are in SI units, so I was good to go. If you aren't sure, then by all means put those units in. Okay? So, 2.8 meters per second squared is your acceleration. Easy peasy. Let's try one a little different. A car starts from rest. Again, I'll underline that. And accelerates at 15 meters per second squared for 3 seconds. What is its top speed? Okay, so let's write out what we know again. We know our initial velocity equals 0. We know our final velocity equals who knows. We know our acceleration is equal to 15 meters per second squared. And we know that our time is equal to 3 seconds. So, taking a look at our original equation, we know acceleration is equal to delta V over T. As I mentioned before you do anything else, let's solve the equation for what we need. So we need to find what V final is. Well, we know that this equation can also be written as V final minus V initial over T. Multiply both sides by T. You're going to get acceleration times time is equal to VF minus VI. If we add VI to both sides, we get VI plus AT is equal to VF. So let's go ahead and use this equation. Then I'm going to put it over here so we have some space. VF is equal to VI, which is 0, plus our acceleration, which is 15 meters per second squared, times our time, which is 3 seconds. Well, that's a simple multiplication. We should end up with 45 meters per second. Notice the units. It's in velocity. So there we go. Simple. Again, for those of you that want to just plug in numbers and then do the algebra, that is something we have to try and get away from, okay? You want to do the algebra first, then plug the numbers in, all right? Let's do number 3. If a snowboarder is traveling 8 meters per second, how long will it take her to reach 36 meters per second if she accelerates at a rate of 3.5 meters per second squared. Well, we're looking for how long will it take her. So, obviously, t is the unknown. But what do we know? Well, we know our initial velocity is equal to 8 meters per second. We know our final velocity is equal to 36 meters per second. We know our acceleration is equal to 3.5 meters per second squared. So, oddly enough, we're going to use the same equation we've used before. Acceleration is equal to delta v over t. Solving for t, we know that t is equal to delta v over a. Plugging in our values, remember delta equals vf minus vi, so 36 minus 8 divided by 3.5. And what do we get? We get a total of 8.0 seconds. So again, if you're following the units, I'll just do a little aside here. You've got meters per second on the top, and you've got meters per second squared on the bottom. Simple fractional math tells us that we should end up with units of seconds. So, exactly what we would expect. This is why we do the algebra, because when we get into unitary analysis, it's going to be really important for us when we're quite uncertain about which equation to use. That's going to help us along. So, 3 simple questions just using acceleration. I'm going to say something very important again. This is uniform accelerated motion. So a lot of people, when they want to find velocity, they'll immediately go to distance over time. As soon as you hear the word accelerated in any form, if there's a change in velocity, you instantly should start thinking, okay, I got to deal with acceleration, delta v over t. Okay? When we were talking about our solutions, we didn't bring up a direction, and all vectors have both a magnitude and a direction. So I've alluded to this before in a previous lesson, but there's this idea that the sign in front of the number actually tells you something about the direction of motion, and it works generally like this. If the object is moving up or to the right, you can call that east if you wish, the numbers are going to be positive. Whereas if an object's moving down or to the left, or backwards, or west, we're talking about values that are going to be negative. So there is a possibility that a velocity and acceleration can be in opposite directions. The prime example of this is an object slowing down. The velocity is still pointing to the right, or pointing east, or pointing in the direction of motion, so it's still positive. However, the acceleration is negative and pointing the opposite direction. Why? Because it's slowing you down. Whereas when we're speeding up from, say, a stoplight, both are pointing in the positive direction. So it's a little tricky. It's a sign convention. You're going to get docked a half every time you bugger that up. So super important that you figure that out. So let's take a look at this particular table right here. Let's start with an easy one. A car is sitting at a stoplight and hits the gas. So what's our velocity? Well, we're moving forward. So our velocity is most certainly going to be positive. And how did we get from 0 to some velocity moving forward? Because we had a positive acceleration. This should not be surprising. Anybody that's been sucked back in their seat in the car totally knows what I'm talking about. Let's start with the second one now. From rest, you back out of your driveway. So this is a direction convention. Now, if forward is into, say, your garage or into your house, then backwards has to be negative. So your velocity is negative because you've associated a direction of forward as towards your house or into your garage. What does that mean about our acceleration? Well, we are also accelerating backwards. So that's another negative. Again, because you are gaining velocity, that doesn't mean you have a positive acceleration. You have a negative acceleration because you are accelerating backwards. Okay, so don't take that as something other than it is. These signs are just direction. A plane lands and comes to a stop. So again, when your plane lands, it doesn't just start moving backwards, it continues to move forward, which means its velocity is positive. Yet you're starting to slow down, which means it's trying to decelerate. So what's that going to be? That's going to be a negative acceleration. If you drop a rock off a cliff, well, think about that. Again, it is increasing in velocity, but our general convention suggests that down is negative, which means our velocity is going to be negative. The acceleration, because it is increasing in velocity going down, also has to be negative. Now this is something that's going to be really useful on the next question, because when you throw a rock straight up, Again, up is positive, so our velocity is positive, but it's slowing down, which means our acceleration is negative. There is a general thing I'm going to tell you now, and it's this idea that the acceleration due to gravity always points to the center of the planet. What does that mean? That means it is always pointing down. So when you're dealing with objects that are in free fall or in flight, when acceleration of gravity plays a role in it, that acceleration is always with a sign negative, unless you have chosen down as a positive direction. So it doesn't matter which way you go, but convention would suggest that it's way more useful if you just consider down negative, up positive, right positive, left negative. So my friends, for those of you with my notes, you've got to try and sketch some velocity versus time graphs for given situations. Give that a go, and I'll take a look at those later. For those of you that don't, practice this stuff. Make sure you got your signs down, and make sure you understand what acceleration is doing to your system. Good luck, and we'll talk to you again.